In the last lecture, we talked about the end of life of a high mass star and how it goes supernova at the end of its life. And you might think that that just completely explodes the star into nothing, or at least into just some big gas cloud like the pretty supernova remnants that we looked at. But in fact, that's what just happens to the outer layers and the shells. The core actually, through all of this, remains intact because of its huge gravity. And in this lecture, I'm going to tell you one of the possible fates of the core of the star. And this is going to be what we call neutron stars. And this is only going to happen if the original mass of the star was between 3 and 8 times the mass of the sun. That's the total mass of the star prior to the supernova. The core itself has to be between 1.4 and 3 times the mass of the sun. In this case, the gravity is ridiculously strong, and it's overcoming the electron degeneracy pressure. There is no fusion to stop it, so there's no thermal pressure. It collapses the star incredibly until it has a radius of only something like 10 kilometers, which is very, very small. If you think about it, that would fit inside loop 610. This is something many times the mass of the sun fitting into a space smaller than the city of Houston. And in fact, the gravity is so strong in this case that the electrons literally get pushed inside the protons. It's not merely that they just attach themselves to the nucleus or something, they literally merge with the protons and form neutrons. That's why this is a neutron star, because the composition of a neutron star is just neutrons. You can't even talk about the elements that make up it because there's no protons anymore. Elements are defined by the protons. It's just neutrons. Now, it does stop collapsing at a certain point when the radius is about 10 kilometers. There's an equivalent to electron degeneracy pressure that neutrons do. That's called neutron degeneracy pressure, and that is stronger than electron degeneracy pressure, so it can support things, it can support greater amounts of gravity. The 3 times the mass of the sun limit that we get is the limit for neutron degeneracy pressure, and later on we're going to learn what happens if the mass of the core is even bigger than that. And you can start imagining where this is going to go. Now, how do we know these things exist? Well, the major piece of evidence for neutron stars is something called pulsars. And what you're looking at in this picture is an actual radio image. So this is taken with a radio telescope, not a normal visible one. And it's a time-lapse sequence. So this is like the frame by frame of a video. And these bright spots are separated by 0.033 seconds. This happens to be in the Crab Nebula, which I showed you in the last lecture, is a very famous supernova remnant. So this was found in the middle of something we know had a supernova, because this is the one that everybody observed except for the Europeans back in the 11th century. Now, when this was first discovered, it was considered kind of surprising, because this was the first really, really regular radio signal that had ever been discovered in space. This was very early in the history of doing radio astronomy, and it was very surprising that we would get these strong pulses that were exactly evenly spaced in time. And in fact, the first reaction that the scientists had to this was kind of funny, because what they thought was that it was aliens. Quite seriously, they thought it was aliens. They even, for a while, called this LGM for little green men before they actually knew what was going on. This was a very, very startling result. Now, eventually they decided it wasn't aliens and they figured out what it was, and this is what we now call a pulsar. A pulsar is a special kind of neutron star. By the way, the scientist who discovered this was a woman named Jocelyn Bell. Now, what is a pulsar? Well, this is a major piece of evidence for the existence of neutron stars. And what you see in the picture here is an artist's concept of what's going on. What you've got is a neutron star. Now, neutron stars have magnetic fields, and in fact, they have very strong magnetic fields. Stars have magnetic fields, like the sun has a magnetic field, and this is kind of the shape that it has. It's very similar to the magnetic field of the sun and similar to that of the Earth, except it's very, very much stronger, because when you compress the source of a magnetic field, the magnetic field gets stronger, and it's strongest at the magnetic poles. Now, what happens is that, of course, this is in the middle of a supernova remnant. There's gas left over after the star exploded. And that gas gets caught in the magnetic fields. And it turns out that whenever gas gets caught in the magnetic field of something, it gives off light, just like we have the northern lights, the auroras on Earth that we've looked at in class, where particles from the sun are getting caught in the Earth's magnetic field, and those give off light. So same kind of phenomenon. Now, the neutron star is also rotating, but the axis that it's rotating on is not necessarily the same as its magnetic axis. For instance, on Earth, you may know that magnetic north is not right at the North Pole. It's even more drastic in the case of pulsars. The axis that it's rotating on is not the same as the magnetic axis. And so as this thing is rotating around, these beams where the light is particularly strong along the magnetic axis will occasionally rotate into our line of sight, and we see a flash of radio waves. The kind of light these things are giving off happens to be radio waves. So whenever it rotates into our line of sight, we see a flash of radio waves, and that's what makes the pulsing feature that we see. Now, not every neutron star is going to be a pulsar. First off, they have to still have gas that they could be getting from to cause the light, but they also have to be lined up in the right way so that this axis occasionally points into our line of sight. So if that never happens, then we don't see it as a pulsar. So just again, here's a sort of picture of it. You might also want to go to this website. This has a nice little simulation that you can watch. But here's the neutron star. It's rotating around an axis like this, so it's going sort of clockwise or counterclockwise, around like that. And sometimes, and this cone is where the light is coming out. That's the magnetic axis. And so here's a really extreme one. So this one's rotating again around, as you can see in the little purple circle. And these are the beams from its magnetic axis. And so you can see here it's pointing towards Earth. We're going to see a flash of light then. But if it rotates so that those beams are here and here, we're not going to see that. So we don't see a flash of light, and that's when it turns off. And because it's rotating at a very regular rate, we know that that's why we get these very regular signals. The speed that these things go around is incredibly fast. It's very, very, very fast. And it turns out that if you do some calculations, you can find out that to produce a rotation that fast, the source of this must be very, very, very small in radius. And so that's how we know that it's a neutron star, is because a neutron star is the only thing that has the right kind of radius to produce this rotation, this amount of magnetic field that is necessary to produce the light that we see with the regular pulses that we see. So this is important because this is how we know that neutron stars actually exist. If it's not a pulsar, neutron stars don't give off light of their own. They are dark. There's no electrons to be jumping around or anything like that. So they're dark, and they're very, very small. So we wouldn't see them if they weren't pulsars. So there could be many neutron stars out there that we have never seen because they don't happen to be pulsars from our point of view.